All right, students, welcome to part 3, SPHS chemistry, acids and bases. Okay, hopefully you guys are getting comfortable with those comprehension checks. Again, if you're having any issues, feel free to contact your teacher. We'll be more than happy to help you in any way we can. To this part is going to be about different acid-base reactions. And in this one, we're really going to be focusing in on the Bronsted-Lowry definition. Because it has a few little unique things in it that are a little different than some of the other definitions that we're just going to kind of focus on. They're kind of important in fundamental chemistry concepts. So when we're looking at acids and bases, many times the reactions, you have these double arrows, meaning it's reversible. They go into equilibrium. So we only have partial dissociation, partial ionization here. So in other words, only a small number of these actually react with the water and go over here. However, as this starts going this way, they get too many over here, then it starts coming back this way. So we have a forward and a reverse reaction going on at the same time, which is why we have the double arrow. It's what we call an equilibrium. Okay? So once you put this in here, pretty soon, I mean within less than a minute or so, as many are going to react. And then as time goes on, more want to react, but then that makes too many over here, so these combine back together and come here. And so then the forward rate equals the reverse rate. So we have a forward and a reverse reaction. So we have to look at the acid-base definition from the Bronsted-Lowry perspective. We have to look at that in terms of left to right and right to left. So when I'm looking at HF, remember, a Bronsted-Lowry acid is an H+ donor. A Bronsted-Lowry base is an H+ acceptor. So when I look at this reaction going left to right, the hydrogen is being donated to the water, and you're being left with an F-, and it's just the H+, and so the H+ goes to the water, making H3O+. And so this is the proton donor, this is the proton acceptor, that makes this the acid, and this arrow needs to be right there. That makes this the acid and this the base, okay? And so this then, now, if we look at it going from right to left, it's going to be the conjugate base. Now I don't know if any of y'all have taken, probably most of y'all have taken some kind of foreign language. And then when you have foreign language, one of the things you do right off the bat is you have to conjugate your verbs. So a star is a stoy, and a stas, and a sta, a stamos, a stan. Okay, all the different forms of the same word. They're all related to one another. So a conjugate is going to be related to the base from which it came, or the acid from which it came. And so HF donates and now becomes F-. Well, F-, since it just lost an H+, it now has the ability to accept one back. Therefore, the F- is now going right to left. The hydrogen is being donated to the F to become HF. So if we're looking at it going this way, the F- is accepting a proton, which makes it a base. But you can see HF and F-, those two are related to one another. So it's the acid and its conjugate base. The conjugate base is the thing that is left over after an acid donates one hydrogen. Okay? So after it gives up a proton, it's the conjugate base. So the same thing as here, water in this case is acting like a base. So water accepted a hydrogen going left to right. So it became H3O+. It accepted. So this is the conjugate, this is the base. The H3O+ over here now, going right to left, it donates the hydrogen back to the F to become H2O. And so now this is my conjugate acid. So this is a base, this is the conjugate acid. You can see these two are two forms of the same thing. It's kind of like the verbs, you know, you just change it a little bit. So, you know, the conjugate acid is the species, the thing that remains after a base accepts a proton, because now it has one that it can donate. So an acid is always going to form a conjugate base, and a base is always going to form a conjugate acid. Acids make conjugate bases, bases make conjugate acids, because once something donates a hydrogen, it now what's left has the ability to accept one back. after one accepts a hydrogen, after the water accepts it, it now has an extra hydrogen that it can donate going in the other direction. So in any acid-base reaction with Bronsted-Lowry, you always have an acid and a conjugate base, a base with the conjugate acid. Okay? Now, so here's the exact same thing we're just kind of talking about from the base point of view. So in every Bronsted-Lowry, we have an acid, conjugate base, a base with the conjugate acid. Okay? So when we're talking about conjugate acid-base pairs, it's the acid with the conjugate base and the base with the conjugate acid. So this and this, notice they're related to one another. They both have F in it. So it's just the different forms. This is the acid, this is the conjugate base. This is what's left after the HF has donated a hydrogen. Water is the base. This is your conjugate acid. Once it accepts the hydrogen, it now has one to donate when it comes back right to left. Okay? Now, that's the gist of this. So you look at it left to right. The conjugates are always on the right. Okay? Acid base on the left, conjugates are always on the right. But this is not a conjugate acid-base pair. This is not a conjugate acid-base pair. It's the acid with the conjugate base or a base with the conjugate acid. Even though we say base with a conjugate acid, it's still together we call it a conjugate acid-base pair. Okay? So there are two conjugate acid-base pairs. It doesn't matter which one it is. We're always just going to kind of put it in this conjugate acid base. So it's not always just the conjugate acid. It's the base with the conjugate acid or the acid with its conjugate base. Okay, so you're always going to have two pair in every reaction. Conjugates are always on the right. Okay, an acid makes a conjugate base and a base makes a conjugate acid. Now, the last thing. Strong acid. So in everything we're doing here, it's kind of always going to be the opposite. Acids make bases, strong make weak. Okay? Now, we said that HF is a weak acid. It's not one of our 6 strong acids, which means it really doesn't want to break apart. The majority of the molecules want to be here. So it's a weak acid. So when the hydrogen is pulled away and it makes F minus really wants to get back with the hydrogen. With the fluorine. Okay? The fluorine and the hydrogen want to get back together. And so it wants to be, it'd much rather be in this form than in this form. So a weak acid is going to form a stronger conjugate base. This is going to want to have a strong attraction to get that hydrogen back. Okay? Water is a very weak base. It doesn't really want, water likes to be water. If water was a strong base, we wouldn't be able to drink. Okay? And so it's a weak base. So once it accepts that hydrogen, this now is a much stronger conjugate. Now it's much more willing to donate. And we know that H3O plus is an acid because we just talked about that. That was what makes an acid an acid. So strong makes weak. Weak makes strong. Okay? Now, if I was to look at HCl plus water goes to, let's go to Cl minus plus H3O plus. Okay? Now, if I'm looking at this reaction right here, we say that 100% of this breaks apart. Every single molecule you put in here breaks apart. What does that mean then about the H and the Cl's attraction for one another? If they break apart 100%, can't be a very strong attraction between the hydrogen and the chlorine. Therefore, once the Cl minus gets rid of the hydrogen and makes H3O plus, this Cl minus, so this is a strong acid. Meaning it ionizes 100%, meaning that the H and the Cl break up easily. So the Cl minus over here, my conjugate base, this is singing the song, we ain't never, ever, 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 never, ever, we getting back together again. Okay? It's not, sorry hydrogen, I just got rid of you, I have no attraction for you, I don't want you back. So this is going to be a very weak conjugate base. Okay? So the stronger the acid means the more readily this bond is broken That means that the weaker this is, because this means, hey, I have zero attraction for hydrogen. It's not happening. I'd rather be here by myself. We're never, ever, 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 never, ever getting back together again. So a strong acid is going to make a weak conjugate base. A weak base makes a stronger conjugate acid. So acids make conjugate bases, bases make conjugate acids, strong makes weak, okay? I wish I had more time to develop that. That's something that's really important. You just have to remember that it's opposites. And it's all about how strongly, how easily do they donate these hydrogens? How much of an attraction does this have for a hydrogen? The stronger the acid, the more readily these break apart. The stronger the base, the more attraction it has for a hydrogen. Okay? And then the pH kind of helps us determine that. So, when I look here, here's acetic acid. Notice how it's changing. Now it's kind of a structural formula. Notice the hydrogen came off the end over here. Okay? But this, to go from here to here, it donated that hydrogen. Well, that hydrogen got donated to the water. So the water accepted the hydrogen, so it's a base. Well, now that the water accepted a hydrogen, it now has this extra one. So if I'm looking at it right to left, this to go from here to here, it's donating the hydrogen back, it's getting rid of it, and so it's the conjugate acid. And this one, to go from here to here, it has to accept the hydrogen, so this hydrogen is going back to it to make this. Now, because it's a weak acid, we know that the majority is going to be here. So we only have a few go over here, and then once you get too many, they all start combining and coming back here because this is the much more favored. Weak acids want to be in this form. Strong acids want to be in this form. Okay? And how do we know if it's strong or weak? We have 6 strong acids. We talked about that in the last part. Okay? And so we just need to know the strong acid. Any other acid is a weak acid. Okay? Now, some substances, fancy word, are amphoteric. That means it can be an acid or a base. Probably water is the most common amphoteric substance. If you put an acid into water, water is forced to accept the hydrogen, making an H3O+, so it's a base. However, if you put a base into water, the water donates the hydrogen to the base, and so it's actually an acid producing the OH-. So, there's not a whole lot of substances are amphoteric, but there are some. We just talked in the previous one, a common base is baking soda. Baking soda is actually, if we look at the formula, is sodium hydrogen carbonate or sodium bicarbonate, NaHCO3-. Now when you put that into water, it breaks up into Na+ and HCO3-. Those are the 2 ions. But if we look at that ion right here, this ion has a hydrogen, but it's also negative. So it could accept a hydrogen and become H2CO3, or it can donate this other hydrogen and become CO3-2-. It can kind of go either way. It's amphoteric. Baking soda helps get your pH of your stomach right because it can act as an acid or a base. It can, if you have too much acid, then it can neutralize some of it. If you have too much base, it can react and help cure that too. And so that's why sometimes if you have an upset stomach, they say to drink a carbonated beverage because there's a bunch of this ion in a carbonated beverage. So like a 7-Up sometimes helps calm your stomach because it has this bicarbonate ion in it. It's amphoteric. It can either accept a hydrogen and go to H2CO3, or it could lose a hydrogen and go to H+ and CO3-2-. So it can either act like an acid, it can accept, or it can donate the hydrogen. Either one. Okay, so that's what amphoteric is. Okay, not a lot of substances are amphoteric, but there are some. Water is probably the most common. Okay, so you can go ahead and pause it now, and you can look and identify your conjugate acid-base pairs here. And so this is multiple choice, just kind of see which one of these are actually a conjugate acid-base pair. Okay, and so you have these 2 all the way through number 6, comprehension check. So go ahead and pause the video and work those out right now. All right. The second type of reaction is a neutralization reaction. This is a review. We already did this when we were writing and balancing equations. We did neutralization. They're double replacement reactions, which means the positive one of the first is going to go with the negative one of the second. The positive of the second is going to go back with the negative of the first. When we write the compounds over here, remember you always write positive first and then negative, and you always have to balance the charge, okay, with your subscripts. So the key is with acids and bases, the positive thing is always hydrogen. The negative thing over on the second on the base is always hydroxide. H plus and OH minus always makes water. I always like to write it as an HOH, okay? HOH because you can kind of see the H plus combines with the OH minus, but you're much more familiar with H2O, so either way you write it, but to me it's easier to kind of balance it, to keep track of your H pluses and OH minuses if you write the water as an HOH versus an H2O. But you can kind of see here that we would need to balance. This one is not balanced, okay? This one is not balanced either. We would need to put a 2 here and a 2 here to balance those equations. And by the time that you get this PowerPoint, that will be corrected on there, okay? So in these types of reactions, okay, that's what I'm saying, it's a neutralization reaction. It's a positive with a negative, so you're going to get some kind of ionic compound, a salt, and water. But again, that's review of things you used to do. We've done before, okay? So this is your Tums. The chalk, actually, if, you know, just I can't help myself, okay? When you take Tums, Tums is actually calcium carbonate, which is chalk. It's a flavored chalk. And when you put that into your stomach, it breaks down into calcium oxide and carbon dioxide, okay? And then the calcium oxide reacts with water in your stomach, and it goes and makes calcium hydroxide. Then the calcium hydroxide neutralizes your stomach acid. You can't just take, you couldn't drink sodium hydroxide because it'll burn you just like acids do all the way down. So you have to do something that's neutral on the way down, and then it reacts in your stomach and makes this calcium hydroxide, which then will neutralize your stomach acid. Magnesium hydroxide is okay to drink because it's not soluble. Remember we said it was a suspension. So none of that hydroxide is soluble up in your mouth or on down your esophagus, but once it hits your stomach, it reacts with the HCl to neutralize the excess stomach acid. So those are just some common examples of neutralization reactions that take place in your body. Now, lastly, mono obviously means one, poly means many. So a monoprotic, remember proton is a hydrogen, so a monoprotic acid only donates one hydrogen. So you only have one hydrogen. If it's polyprotic, it means you can have more than one. If it's diprotic, it's got 2 hydrogens. And if it's triprotic, like phosphoric acid, it has 3 hydrogens to donate. Now what you need to know on that though, is that when di and triprotic acids donate, they don't donate both of them at the same time. They do one at a time. So if you started, you just put this into water, it's going to break up into this. Then once all of these have gone to that, then these start going to here. If you're doing a neutralization reaction and you only put half the amount of base in, you're going to end up only getting to here. You don't take 2 off of some and 0 off of the others. They all lose one, and then they'll all lose the second one. It does it in stages. So if you look at nope, I thought we had a phosphoric acid on there. If we used phosphoric acid, H3PO4, there would be 3 steps. And so each hydrogen comes off one at a time. But in a base, a monobasic base, and that's kind of redundant, but that's the only way to say it, you just have 1 OH. In a dibasic, you have 2 OHs. Okay? There aren't hardly, I know of very few tribasics, but it'd be the same. But regardless, unlike acids, the only way these can dissolve is as ions, so they just break apart completely, and so you don't do it in stepwise with bases, but only with acids. After you donate 1 hydrogen to HSO4, 2 hydrogens, so it's a stepwise process. Okay, so that's the most important thing on that. Okay, so now here's your final comprehension check for this unit, for this part of the unit, I should say. And so stop now and do that, and this was a quick and easy little section. And again, if you have any questions, feel free to ask or email your teachers. All right, that's the end of part 3.